Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 6, Complex Numbers. You've seen complex numbers used by several different blocks in GNU Radio. I'd like to tell you all about why complex numbers are used in digital signal processing, and in particular in Software Defined Radio. I'd also like to show you how complex numbers can be used to explain the various DSP mysteries that we've encountered so far. But first we need to have the talk about complex numbers. Now perhaps you're familiar with complex numbers and imaginary numbers, and perhaps you're not. Either way, I'd like to show you how I think about complex numbers. Now personally, I first learned about complex numbers in school, and then I forgot about them and thought I would never see them again for the rest of my life. Then I started doing software-defined radio, and I quickly discovered that complex numbers were something that I would have to get familiar with again. So I made a deliberate effort to relearn complex numbers, and I learned how to conceptualize them in a way that makes sense to me, and I hope will make sense to you. When I think of numbers, I like to visualize them on a number line. For example, 0, 1, 2, 3, and so forth. Every number is a point along a line. And I think of addition like this. If I were to take 1 plus 2, that's starting at 1, shifting over 2 spaces to the right, and ending up at 3. Or let's say 2 plus 3. That's starting at 2, shifting 3 spaces to the right, and ending up at 5. And I think of subtraction in the same way, except we shift the other direction. So 6 minus 2, we start at 6, shift 2 spaces to the left, and end up at 4. Or let's say 8 minus 5. That's starting at 8, shifting 5 spaces to the left, and ending up at 3. In other words, I think of both addition and subtraction as a way to translate or shift to the left or right along the number line. Now, how about something like 3 minus 5? Can I subtract a bigger number from a smaller number? You'd probably say, sure, all you have to do is extend your number line to the left and end up at the result of negative 2. But the existence of negative numbers hasn't always been obvious to people. Mathematicians argued over the legitimacy of negative numbers for centuries. And you can imagine why. They're a little bit different. They're a little bit more of an abstract concept than positive numbers. For example, if I walked up to you and I said, I have 2 apples. Do you want one? You would say, sure, and I'd give you an apple, and then you'd know that I had 1 apple left. But what if I walked up to you and I said, I have negative 3 apples. Do you want one? What would that mean? How many apples would I actually be carrying? Do I owe somebody some apples? Could you ask me for a negative apple? How does that work exactly? It's a little bit of an abstract concept. And you can understand that people had to make a leap of reasoning to start to accept that negative numbers were legitimate numbers, just like positive numbers. So let's pretend that we haven't come to that conclusion. Let's pretend that we don't know anything about negative numbers. How might we decide how to handle this problem of 3 minus 5? Now, you know that you can add any 2 numbers together. As long as we agree that we can extend this number line arbitrarily to the right, then we can add any 2 numbers together and keep adding and have no problem. But when we subtract, we do sometimes run into a problem where we might want to go off the left edge of this number line. So let's see what happens. If we take our visual approach, our geometric interpretation along the number line here, then 3 minus 5 would look like this. We'd start at 3. We would shift over 1, 2, 3, 4, 5 spaces to the left, and we would end up right about here. That suggests that we've gone 1 and 2 spaces to the left. So maybe we could extend this all the way. Who knows? Maybe it goes forever. Maybe we could have 1, 2, 3, 4, 5, and so forth. Now this, we might number them. 1, 2, 3, 4, 5. However, this is confusing because now I have 1 and 2 and 3 and 4 on the left, but I have 1 and 2 and 3 and 4 on the right, and I have to have some way to distinguish one direction from the other. Well, maybe if we look at our numeric, our arithmetic version of this down here, this might give us a clue as to how we could represent this. Now, how could we simplify this expression, 3 minus 5? One way we could simplify it would be by changing it to 2 minus 4. Now, that should end up in the same place, right? We would go 2 and shift 4 spaces to the left. 1, 2, 3, 4. And we'd end up there, 2 spaces to the left of the origin. If we continue to reduce this, it could be 1 minus 3, or it could be 0 minus 2, and now we've reduced this term as far as we could go. In fact, a 0 is nothing, so we could just erase that. And what we're left with is minus 2. So that suggests that what we should call this number over here on the left is minus 2. That's how we should designate that it's different than this 2 over here on the right. And it suggests that we should call all of these things negative numbers, or minus 1 through minus 7 and so forth. And this is, I like to think that this is a kind of approach that people might have taken long ago to come to the conclusion that negative numbers were legitimate. And the reason that we can tell that they're legitimate, I think, is that this visualization and this arithmetic interpretation are completely consistent with one another. The idea that we can translate numbers to the left or right by adding or subtracting completely agrees with all the arithmetic we can do once we understand that negative numbers exist. So let's think about multiplication for a moment. How would we multiply 2 by 3? Well, we would start here at 2, and then we move over. Are we translating 4 spaces to the right? No. You know the answer is 6, but it's not a translation. The way I think of it is that we have this arrow that extends from 0 to 2. It goes from the origin 2 spaces to the right. And then we're taking that 3 times. So we go 2 spaces to the right once, and then twice, and then 3 times. We triple this distance from the origin and end up at 6. Or take, for example, 1 times 4. We start at 1, and I think of that as being an arrow that goes from the origin to 1. And we take that arrow 4 times. Once, twice, 3 times, 4 times, and we end up at 4. In other words, multiplication allows us to scale a number. We scale its distance from the origin, from 0. It's scaled, not translated. And what about multiplying by a negative? If we were to, say for example, take 2 times negative 3. Well, we'd start at 2, and you probably know the answer already. It's negative 6, right? But how do we get there? The way we get there, the way I like to think of it, is that we take this arrow, this vector that goes from 0 to 2, we triple its length, or scale it. And we scale it by 3 times because we're multiplying by something that has a distance from the origin of 3. So we take that once, twice, 3 times. We end up over here at positive 6, but then we flip it around. We rotate it, and we end up at negative 6. That's interesting because it suggests that multiplication does something more than scaling. Multiplication can scale a number, and it can also rotate a number, or flip it around the axis. Flip it around the origin, I would say. How about taking a number like -1 and multiplying it by a negative number, -5. Well, I think of that as starting at -1, or having this arrow that points in this direction. And we're going to scale it 5 times. So that's once, twice, 3 times, 4 times, 5 times. And then from here, I'm going to flip it around because I'm multiplying by a negative number. I'm going to flip it around and rotate it over to +5. Now, we rotate by a half turn when we multiply by a negative number, or we rotate by no turns when we multiply by a positive number. So we can rotate either a half turn or no turns. Now, multiplication and division both work the same way, except in one case we're scaling up, and in another case we're scaling down. So both multiplication and division can scale and rotate. And of course, addition allows us to translate, and subtraction allows us to translate. So just using these very basic arithmetic operations, we can scale, rotate, and translate. And I think that that fully describes all of arithmetic. Now, can we translate by an arbitrary amount in either direction and end up anywhere on this number line? Sure. Can we scale by an arbitrary amount and end up anywhere on this number line? Sure. Can we rotate by an arbitrary amount and end up anywhere around the origin? Well, that's an interesting question. We can certainly rotate by a half turn, and we can rotate by no turns, or you might think of that as rotating by a full turn. But can we rotate by, say, a quarter turn or an eighth of a turn? I'd like to approach this question by playing another game of what if. What if it is possible to rotate a number by multiplication to some place that is not on this number line? Can we rotate? We know that we can rotate, for example, 2 times -1. We know that multiplying by -1 rotates us a half of a turn, and that equals -2. But is it possible to rotate by less than half a turn? Let's say we could multiply 2 by some number that rotates us a quarter turn. Well, if that were true, then we should be able to rotate again by the same amount, the same quarter turn, and end up over here. In other words, if we were to say 2 times some mystery number z times that mystery number z again, we should end up at -2. Is that possible? Well, let's check this out. If we were to just solve for z here, we'd see z squared equals, that's -2 over 2, so that's -1. In other words, z is equal to the square root of -1. So apparently, the square root of -1 is the amount that we have to multiply by in order to rotate a quarter turn. Well, that's interesting. At some point in your mathematical career, somebody might have told you that there's no such thing as the square root of -1, but we seem to have just discovered it here. Let's try a different one. Let's try starting at -3. If we start at -3 and rotate a quarter of a turn, and then rotate a quarter of a turn again, we should end up at +3. So -3 times some mystery number z times z again should get us to +3. Okay, if we solve for z, we get z squared equals, well, that's 3 over -3, which is -1. And so again, we find that z is equal to square root of -1. It's consistent with the answer that we got trying a different case. That's a good indication that we might be onto something here. So if this number, the square root of -1, exists, where is it on our number line? Well, here's a trick we can use to find it. What if we were to take 1 times the square root of negative 1? Sorry, it's supposed to be times square root of negative 1. Now 1 is the identity, the multiplicative identity, but we can also use our geometric interpretation here and say we're starting at 1 and we're rotating by a quarter turn, because that's what the square root of negative 1 gets us when we multiply by it. So we rotate a quarter turn and we end up right here, which suggests that this is the exact location of this number, the square root of negative 1. And if we were to multiply that number by 2, where would 2 times the square root of negative 1 be? Well, it would be scaled from the origin, so it would be right here. Aha! This suggests that we could have any number of multiples of the square root of negative 1. We could have 1 here, here's times 2, here's times 3, here's times 4, and here's times 5, and so forth. That's pretty interesting. It's a completely different axis than the axis that we're used to. And if we were to multiply those numbers by negative 1, then presumably we should find that we can also have numbers going down this axis here, or this lower extension of the vertical axis. And here's 1, like negative 1 times the square root of 1, and negative 2 times the square root of 1, and negative 3 times the square root of 1, negative 4 times, negative 5, and so forth. Now, the square root of negative 1 is referred to by mathematicians as I. It's called the imaginary unit. And this axis is called the imaginary axis. This axis, this horizontal axis, is called the real axis. And numbers that you're used to, positive and negative numbers, are called real numbers. Numbers that are on this vertical axis are called imaginary numbers. Now, to make things more confusing for you, some people also call this number J, especially electronics engineers, because I was already taken. And in many programming languages, I've seen J used as an imaginary unit. For example, in Python. So sometimes this number is called the square root of negative 1, sometimes it's called I, sometimes it's called J, but in any event, no matter what you call it, it lives right there. And this is 2i, 3i, 4i, 5i. This is negative I, negative 2i, negative 3i. Notice that when we multiplied negative 3 by I, we ran right through that point. Negative 4i, negative 5i, and so forth. Now, is it possible to rotate by other amounts? We've rotated by a half turn, we've rotated by a quarter turn, but could we rotate by, let's say, an eighth of a turn? Well, I think we could play the same exact game. Let's say we started at 4. We wanted to rotate an eighth of a turn to here, and then rotate another eighth of a turn would get us to 4i. So we could play the exact same game and say 4 times some mystery number z times some mystery number z again equals 4i. And we could solve and find out that, yes, in fact, we can have a number that is right here that is not on either axis. It's not a real number and it's not an imaginary number. It has some real component and some imaginary component. And we call these numbers complex numbers. Really, anywhere in this entire plane, we could have a number, and it would have some real component and some imaginary component. If it's on the real axis, then we also call it a real number, and it has a 0 imaginary component. If it's on the imaginary axis, then we call that an imaginary number, and it has a 0 real component. But all of these numbers, anywhere in the whole plane, including on these axes, is something that we call a complex number. Another way that we can arrive upon numbers that are complex but are not on either axis is by translating by addition or subtraction. Take, for example, 1 plus 2i. Well, we would start at 1 and translate 2 spaces in this direction and end up right here. Now, how do we reduce this? 1 plus 2i? Well, there is no way to reduce that further. It's always going to be 2 terms. And that's what happens with complex numbers. We call them complex because they have those 2 different components, a real part and an imaginary part. Well, let's just make sure that things are consistent here, that we can do things like addition and subtraction and multiplication and division. What if we were to take this number, 1 plus 2i, and let's say multiply it by I? Well, algebraically, we would say that's I plus 2i squared. But remember that I squared is -1. So really this is I minus 2. And we usually write the real part first. So that reduces to -2 plus I. So we would go over 2 and down 1, up 1 to I. And this is the result. So we multiplied 1 plus 2i, which was over here, and we multiplied it by I and got to -2 plus I. Now let's make sure that our geometric interpretation is correct. Multiplying by I should be a rotation of a quarter turn. And if we were to look at this as a vector going from the origin to that point, and then we look at this one as a vector going from the origin to that point, hey, sure enough, that's a right angle, or a quarter turn. So all we did when we multiplied by I was that we rotated this point by a quarter turn. We end up the same distance from the origin, just rotated. And the algebraic interpretation agreed with our geometric interpretation. That's a very good sign. Now let's try taking this point. We have this point -2 plus I. And if we were to take that and let's say subtract something, let's subtract 3i. Well, -2 plus I minus 3i, that's minus 2i. So if we subtract 3i, we should end up at -2 minus 2i. Or the geometric approach, or the interpretation here, our visual interpretation, is that we should be shifting down 1, 2, 3 spaces and ending up here. Sure enough, that agrees with our algebraic result of -2 minus 2i, which is this point right here. What if we were to take this point and multiply it, let's say by a number that is 1 plus 2i, the number that we started with? Well, -2 times 1, that's -2. -2 times 2i, that will be -4i. Now -2i times 1 is minus 2i, and -2i times 2i, that's minus 4i squared. Now these terms can combine in the middle here, so we have -2 minus 6i minus 4i squared. But remember that I squared is -1. So really this is -2 minus 6i plus 4. And then we can combine the two real terms and end up with +2 minus 6i. Well, +2 minus 6i, where is that on our number line? Well, that's positive 2 and we shift 6i downwards, we end up right here. And think about the geometric interpretation for a moment here. We started with this number over here, minus 2 minus 2i. And we can think of that as a vector that goes from the origin to that point. We ended up over here, this vector goes this way. And it looks like we have scaled and rotated our starting vector. And the amount we rotated it was a little bit less than a quarter turn. Well, guess what? We multiplied by this number that is a little bit less than a quarter turn from the real axis. And that's where we normally measure angles from, is from the real axis. So what we did was we took one number and rotated it by the angle of the other number. That's very consistent with what we've seen before with rotations. Or another way to think of it is that we've added the two angles together. We have this one angle, and then we have this angle to the other number, and then we added those angles together and got this big angle to this vector. Now notice, in addition to rotating, we also scaled. We scaled by the magnitude of this vector 1 plus 2i. This number 1 plus 2i has a magnitude greater than 1, so that means we scaled it. Its distance from the origin is greater than 1. So we scaled it, and it became, the number here became bigger when it was multiplied by the number over here. Pretty interesting, huh? And I think that if we were to continue this exercise, you would find that you could add, subtract, multiply, or divide any complex number by any other complex number, and you would find that the algebraic interpretation completely agrees with this visual interpretation. That's an extremely good sign that our concept here of complex numbers is consistent, and it's totally consistent with our concept of real numbers. Now, negative numbers, as I mentioned before, were not accepted for a long time, and even just a few hundred years ago, mathematicians called them things like absurd or fictitious. They eventually accepted them, but only about 100 years or 200 years ago did mathematicians finally agree upon the legitimacy of negative numbers. And I think that if you are to accept negative numbers as being legitimate, then you should also accept complex numbers as being legitimate. Now, I don't like the terminology very much. We call them complex, and we call these numbers on the vertical axis imaginary. I think that calling these numbers imaginary is a slight against them, and it would be nice if we had different terminology. But these terms are very well established, and it's not something that we're going to change overnight. I think that calling them imaginary makes them seem less legitimate, but I think that they're perfectly legitimate. Also, calling them complex. Now I can see why people call them complex numbers, because they have two parts instead of one part. That makes them more complicated. But they're not that much more complicated. It's just one additional axis. And I think that calling them complex scares people away from them. People think, oh, they're complex, they must be difficult to deal with. They're not very difficult to deal with. They take a little bit of getting used to, that's for sure. But I think you'd find that just knowing a little bit of arithmetic and very elementary algebra, and knowing this geometric or this visual interpretation, if you know these things, then you can easily master complex numbers. They're not that hard. Now let's zoom in on the unit area. So this is 1, and this is I, and so forth. What if we were to take this number I and multiply it by I? Well, we would start at I, and we would rotate around a quarter of a turn to -1. And of course that makes sense algebraically, because I is the square root of -1, so I times I equals -1. What if we were to take that result and multiply it by I? We'd rotate around a quarter of a turn and end up at negative I. What if we were to take that result and multiply it by I? We'd rotate a quarter of a turn and end up at 1. What if we were to take that result and multiply it by I? We'd rotate around a quarter of a turn and end up at I. What if we were to take that result and multiply it by I? We'd rotate around a quarter of a turn and end up at negative 1. What if we were to take that result and, okay, you see what we're going to do here. We're going to keep going around the unit circle, around and around. Every time we multiply by I, we go around another quarter of a turn, and then this can keep going forever. Now, there's a name in mathematics for multiplying by the same thing over and over again. And it's exponentiation, or raising something to an exponent or to a power. We take I to the first power, I to the second power, I to the third power, and if we increase the exponent, we go around and around and around the circle. That's pretty cool, isn't it? It's very rare in mathematics that we have such a simple way to create a function that repeats itself, to model, potentially, periodic phenomena with such a simple method. Now, we can do this with other numbers. For example, let's take this one that's 3/8 of the way around the circle. Let's call that z. Well, if this is z to the first power, its angle is 3/8 of a turn from the positive real axis. So if we multiply by z again, then that means we go around the unit circle 3/8 of a turn to here, and that's z squared. If we were to multiply by z again, we would go around 3/8 and end up over here. That's z cubed. If we were to multiply again, 3/8 of the circle is over here, z to the fourth, z to the fifth would be over here. We keep going around and around and around the circle. And we could choose numbers that aren't even on the unit circle. If we chose a number, say, right here, well, the next number would have this amount of angle more than where we started from. If this were z to the first, well, z to the second would be about that much of an angle, but it would be a little bit further out from the origin because z has a magnitude or a distance from the origin that's greater than 1. So we would scale and rotate. So that would be z squared. Z to the third would be out here somewhere, and z to the fourth would be out here. We would spiral out away from the origin. What if we had a number that was inside the unit circle? Well, the next one would be here, and the next one would be here. It would spiral in towards the origin. But if we choose a z that is on the unit circle, any number that's on the unit circle, and exponentiate it, we will always end up with another number on the unit circle. And if we increase the exponent, then we just go around and around and around and around. Now, let's say we start here, and let's say we increase the exponent over time. So I want you to imagine a new axis, a third axis, coming out of the screen right at you. And we're going to progress along this axis. So this first one is right on the screen. The second one is a little bit closer to you. This third one is a little bit closer to you. And each one gets a little bit further closer to you away from the screen. And they're getting closer and closer and closer to your face. As we increase this exponent, what figure are we tracing in 3 dimensions? Can you visualize the shape in 3 dimensions as every one of these x's gets closer to you?
It's a helix, just like this toy.
Let's choose a z, or a base, that is just 1 degree of rotation around the unit circle. So this is z, or z to the first power, and that's 1 degree around the circle. If we square z, we'll go 1 degree further. It's kind of hard to draw here, but this number z squared is 2 degrees around the circle. Z to the 45th power is right here. It's 45 degrees around the circle. Now where would z to the 180th power be? It would be a half turn around the circle to this point right here. Z to the 180th power is 180 degrees around the circle, and of course z to the 180th is equal to minus 1. Now what's z to the 360th? It would be 1 complete turn around the circle back to the positive real axis. 1 is of course equal to z to the 0th power, because anything to the 0th power is 1, and that's equal to z to the 360th power, and it's equal to z to the 720th power, and we could keep going on and on and on, around and around and around the circle, and keep finding larger and larger exponents that would give us the same results that we got with smaller exponents, because this function is periodic. And this particular z would be a convenient base to use if we wanted to use this complex exponentiation to represent degree measure in the complex plane. But it's not the base that most people use for this sort of thing. The base most people use for complex exponentials is right around here somewhere. We'll call that z. If that's z, then z squared is over here, and z cubed is here, z to the 4th, z to the 5th, z to the 6th, and when we get back to the positive real axis and make a complete turn, that's z to the 6.283185, etc. And some of you are probably saying, aha, I know this number 6.28318, and so forth. That number is tau. Now some of you might be saying, tau, I've never heard of this number tau, but I bet you've heard of this number by a different name, and that name is 2 pi. Now if you haven't heard of tau before, I recommend reading the Tau Manifesto. It will tell you all about why all the cool kids are using tau these days instead of pi. But just remember that when I use tau, I just mean 2 pi. It's the exact same thing. Now the reason that it works out that tau of exponent is equal to 1 complete turn of rotation is because this arc length, this amount of circumference from 1 to z, is equal to 1, or it's equal to 1 radius. In other words, the angle of z is equal to 1 radian. And radian angle measure is of course preferred by all sorts of people, scientists, mathematicians, engineers. Everyone likes to use radian measure instead of degree measure. And this particular z happens to be equal to e to the I, where e is Euler's number, 2.71828, and so forth. You might have heard of this number before. And it works out that e to the I theta, let's just designate some number here, e to the I theta is the number along the unit circle that has angle theta with respect to the positive real axis. That's a very special thing to remember, e to the I theta, or e to the I of whatever angle you want in radians. So for example, z squared, that's e to the I squared, and following the rules of exponents, that's e to the I times 2, or e to the 2i. And of course, this number, if we were to take a complete turn around the unit circle, this is e to the I tau. That equals 1. a half turn around the circle is e to the I 1/2 tau. Oh, that's interesting. A quarter turn around the circle is e to the I 1/4 tau. Do you see how easy it is to use tau here? A quarter turn is a quarter tau. Now, the pi people are fond of pointing out that this number over here is e to the I pi. That's -1. And they usually rewrite it as e to the I pi plus 1 equals 0. And they say, look at that. Is that not the most beautiful equation in all of mathematics, relating all these fundamental numbers to each other? And I say, well, this one is more beautiful. I mean, it relates all these fundamental constants to unity. What could be more beautiful than that? Now, if you look through the literature, the digital signal processing literature, or really any literature of any subject that studies periodic phenomena, you'll see all sorts of equations with terms that look like this: e to the I 2 pi ft, stuff like that. And it might look scary at first, but keep this in mind. This is a constant, this is a constant, this is a constant, this is a constant. This probably is frequency, that's a constant. And all we're doing is taking some number on the unit circle and exponentiating it over time. It's a helix. This whole big scary term is just a helix. And you'll see these all over the place. So don't be scared of those. Every time you see e to the I something, it's a helix. Now, remember the unit circle from trigonometry? If you studied trigonometry, you might have been presented with something like this, where you saw this angle theta going to a point along the unit circle, and you might have been shown that this distance along the horizontal axis was cosine of theta, and this distance vertically to that point was sine of theta. And you might have even been told that that's how cosine and sine are defined. And it turns out that this works out quite nicely with e to the I theta. In fact, e to the I theta is equal to cosine theta plus I times sine theta. And this result is quite interesting. That is called Euler's formula. It's one of many things that is named after Euler. And it relates e to the I, it relates the complex exponential to cosine and sine. Now, one way to think of this is if you visualize, remember a helix that's going around and around and around the circle. If you imagine this coming out towards you, away from the screen, and then you imagine, well, what is the real part of each of those numbers as we go around and around and around the circle? Well, the real part starts at 1, and it kind of slowly starts towards 0, and then it speeds up, and then it goes towards -1, and then it slows down, and then it goes back towards 0 and speeds up, and then it slows down, and then it's back here at +1, and then it goes back and forth as the helix goes around and around and around and around and around. This is easier to see in 3 dimensions. If you look at a helix and you look at it from the side, it looks sinusoidal. If I look at it from this direction, it looks like a cosine wave. And if I look at it from this direction, it looks like the same thing, except it's shifted. It's a quarter of a period out of phase, or a quarter of a turn out of phase. Notice that I've actually changed the orientation that I'm viewing it from by a quarter of a turn. Now, I'd like you to do me a favor, just a tiny little favor for the rest of your life. Every time you see something that looks sinusoidal, imagine the 3rd dimension. Imagine that it is a helix instead of seeing it as a 2-dimensional figure. Now, here's something your trigonometry teacher probably didn't tell you. The most useful application of trigonometry is the study of periodic phenomena. That's the reason why people consider trigonometry to be an important field of study. It's because it's so useful for periodic phenomena. But here's something else your trigonometry teacher probably didn't tell you. You can use complex exponentials instead of trigonometry for the exact same applications. And if you just get comfortable with complex numbers and comfortable with the algebra of complex exponentials, you don't have to use trigonometric functions at all, and you never have to memorize any of those trigonometric identities that you might recall from your trigonometry studies. Now, I want to point out that there are two completely different ways that people represent numbers in the complex plane. One is in rectangular coordinates. In other words, this point is 3 to the right and 4 up, so it is 3 plus 4i. Or you could represent that in Cartesian notation, 3 comma 4, but I recommend using the algebraic notation, 3 plus 4i. And that's called a rectangular coordinate because we're describing that point in the complex plane by its horizontal and vertical components. Now, another way that people sometimes represent complex numbers is in polar coordinates. They tell you what the distance from the origin is. You might call that a radius, or r. And then they'll tell you what the angle is. I'll call that theta, from the positive real axis. And sometimes people notate this as r at an angle of theta. But really that's just shorthand for r times e to the I theta. Remember, e to the I theta describes a point along the unit circle, right around here, that has that angle. And then we multiply that unit vector by r, and that gets us out to this point here. So two completely different ways to represent the same number. You can do it in rectangular coordinates, and sometimes people will say a plus bi or something like that, or in polar coordinates where you use r times e to the I theta, or r at an angle of theta. And sometimes polar coordinates are more convenient than rectangular coordinates, and at other times rectangular coordinates are more convenient than polar coordinates. For example, rectangular coordinates are quite convenient for addition and subtraction, but polar coordinates are quite convenient for multiplication and division. Now, unfortunately, there are a lot of different terms that mean the same thing when people talk about complex numbers. For example, the distance from the origin. Now, I've called this probably 3 or 4 things already just today. I've called it the distance from the origin, I've called it a radius, I've called it probably a magnitude. It's also sometimes called a modulus, and it's sometimes called an amplitude. It's amazing how many different words we have for the same thing. But this r here could be referred to in any of these different ways. It's also referred to as the absolute value. Now, you've probably heard of absolute value before in the context of real numbers. Of course, the absolute value for a real number is its distance from the origin. And we use the same terminology sometimes to refer to the distance from the origin of a complex number. And in fact, in Python, for example, in Python you would use the absolute value function to give you a point's distance from the origin, any point in the complex plane. And we also have multiple words that refer to the angle, like this angle theta. The angle is sometimes called an argument, and it is also sometimes called a phase, although usually when people say phase, they mean something a little bit more specific than just the angle from the positive real axis. But any of those three words in certain contexts could mean this exact same thing. And we even have multiple words for a number itself. Now, I call this number, this point, I just call it a number or a complex number, but sometimes I might call it a vector because I'm specifically thinking of it as this vector that points from the origin to that point. Sometimes people call it a phasor, although most of the time when they use the word phasor, they're talking about a vector that is rotating around the unit circle or rotating around the origin over time. But all of those numbers can, in some contexts, mean the exact same thing. All of those names can mean the exact same thing. They can refer to a complex number. There's one completely different set of terms that you should know before we finish, and that's the terminology of quadrature signals. And this terminology comes from signal processing and electronics. The horizontal axis is called in phase, and the vertical axis is called quadrature phase. And the thing that can get confusing is that these are typically abbreviated. So the horizontal axis is called I, and the vertical axis is called Q. Now, do you see what can be confusing? I is what you can think of as the real axis, not the imaginary axis. Fortunately, this I is capitalized, and the imaginary unit from mathematics is always lowercase. Now, you'll hear people talk about I and Q sometimes, or they'll talk about IQ samples, or they'll talk about a quadrature sampling system. For example, HackRF is a quadrature sampling system, and it delivers samples to the host computer one at a time. I followed by Q, and then the next sample's I followed by Q. It delivers this stream, I, Q, I, Q. And let's say the first I was 2, and then the next Q was 3, and the next I was -2, and the next Q was 4, and so forth. If that were the case, then you could think of this first I and Q being a complex number 2 plus 3I. And you could think of the next pair, I and Q, as being -2 plus 4I. It's just a different way to refer to something that can be thought of as complex numbers. For homework for this lesson, I'd like you to write a small computer program. You can write it in any language that you choose. And if you're not a programmer, that's okay. Take a look at the exercise and think about how you would approach the problem. What method could you use to solve the problem, even with pencil and paper? And think about what method you could use that would actually work for all different inputs. Now, the exercise is adapted from an exercise in Practical Signal Processing by Mark Owen. It's my favorite introductory book to digital signal processing. So thanks to Mark Owen for writing such a good book and for teaching me this exercise. Go to greatscottgadgets.com/SDR and take a look at the Lesson 6 homework. And that's where you'll find the exact problem that I'd like you to solve. I hope to see you next time in Lesson 7.